Everyone, welcome to another video. Today we're going to be looking at how to calculate normal probabilities. Because in the last video we did find some probabilities of normal curves, but they were when we had when it was exactly -1 standard deviation to +2 standard deviation, if they fell exactly on a standard deviation. And of course, in real life that rarely happens. Um, and so what we normally do is we normally use the probability density function. That was the function that we looked at yesterday, in the previous video. And the calculator can do that all for us. And so it just integrates that function between A and B, so between a lower bound and an upper bound. And so you've got it there that if to find a probability of x falling between two values, A and B, we just use the CAS and we just use the normal CDF function. And I'll show you how to do that in a second, where A is the lower bound and B is the upper bound. And it's just integrating that function we looked at in that last video between the values of A and B. This is a really simple process, and I'll show you this in a second. Okay, so for that first question there, let's have a look. And so in a method sack, the mean was 58.3%. So the average score was 58.3%. And the standard deviation was 9.2. So remember, standard deviation is on average, how far are the data points away from that mean of 58.3. So 9.2% is the average distance from the mean. Let X be the number of just a random student's SAC score. Okay, so what's the probability that a random student scored between 50 and 70 is the first question. So on our calculators, we go to menu, we go to probability, and we want distributions. And for this one here, we want the normal CDF. So that's that second function there. And so we just literally put in your bounds. So here we want between 50 and 70. So our lower bound is 50, upper bound is 70. Our mu, so our average here is 58.3. So put in your average value, and your sigma, which is your standard deviation, was 9.2. So just fill out all that information and it pops out your answer, which is 0. Let's just do it to 2 decimal places. So that's equal to 0.71. It's as easy as that. I'll just show you a couple of other ones. Probability x greater than 8.5. So menu, probability, distributions, normal CDF. Here we want our lower bound to be 85. And we want our upper bound. We want to go to infinity. We want it to go forever. So upper bound. So to find infinity on your calculator, you go to the pi menu. So pi down here, if you can see where my mouse is, and then enter in infinity. So we want the values to go from 85 just to keep going forever. Okay. So we want to cover all of them. Don't put in 90 or 100, whatever. You need to go, well, actually you could do 100, okay, but in this case, because it's a percentage, so that actually doesn't make sense. But for today, we'll just make it to infinity. Mu again was 58.3, and our standard deviation was 9.2. Okay, and so that's a very, very low, very low probability of getting greater than 85% in this SAC. So that's 0.00, let's do 19. Okay, so that's the probability of getting greater than 85. We'll just do one more. What's the probability of getting less than 30? Probability, distributions, normal CDF. We want it to go, already got the negative infinity in there, which is nice, up to 30 and 58.3 and a standard deviation of 9.2. I think I know that one now. And again, a very low probability that a student gets below 30. So that's 0.001, let's call that. So hopefully that makes sense. That's just using the calculator to get probabilities. And you see that's much easier than what we were doing in the last video, doing all by hand. So that's 68, 95, 99.7% rule. That's good for approximation when that's all we've got. But if you've got the calculator, way, way, way easier to be able to calculate those exact probabilities to 4 decimal places or whatever the question asks for. Now, just the last thing in this video I want to have a look at is how do you compare two distributions? Okay, so I'll just jump straight down to the example down there because this will sort of help sort of explain what we're talking about here. Let's say you've got year 7s, right? And we're doing high jump. And let's say that on average, year 7s jump 1.2 meters, and they have a standard deviation of 0.2 meters. And year 10s, because they're much bigger, much taller, much stronger, then their average jumping height for high jump is 1.5 meters with a standard deviation of 0.3. And so let's say we've got Jane, she's a year 7, and she jumps 1.45 meters in her competition. And she's got her sister Emily, who's in year 10, and she jumps at 1.83 meters. So the question is, who is a better jumper for their age? Who did better in the competition? And it's really hard to answer these sorts of questions because, well, Emily's jumped higher, but is that, way better? The average for her age group was 1.5, but the average for Jane's age group is 1.2. So who actually did better? Could we just say, well, 1.45 is, 25 centimeters higher than 1.2, and so is that good? And then, but Emily is 1.83, so that's 33 centimeters higher than average for her age group. So isn't that better? Well, the way that we can actually compare to normal distributions is by making it standard. We're going to standardize those distributions. And let me just talk a little bit about this. We call a standard normal distribution, we call it Z. And what Z is this standard thing, and it's got a mu of 0. In other words, if we draw a bell curve, then 0 is in the middle. 0. Oh, it's not going to draw it because it's like way down there. 0 is in the middle, and the standard deviation is going to be 1. Okay, so it's going to be +1 there, +2, that'll be -1, -2. So this is the simplest a bell curve and the means and the standard deviations can get. Okay, and so that would be what Z looks like there. So it's called a Z score that we give it, and that tells us really what the Z score tells us is how many standard deviations is that score above the mean. Okay, and so that's really key. You go, well, you got a Z score of 2. That means you're 2 standard deviations above the mean. That's really high. Or you might be, or your Z score was -1. That means that you're 1 standard deviation below the mean for that, and that gives you a bit of an idea about where you sit, and that allows us to compare two different tests, two different distributions. Really helpful in research and in all sorts of psychology and science and things when we're trying to compare two things which are very different. Okay, I hope that sort of makes sense about sort of being able to understand how we sort of how we're using these. And I'm trying to erase these things, but they're not erasing. Oh, yeah, that's sort of. I'll remind myself not to do dotted lines next time. So let's also, the other thing is how do you calculate a Z score? And if you think about it, if we're taking the distribution and we're trying to get back to a mean of 0 and a standard deviation of 1, then what we do is we get the X value. We get that X value, we subtract the mean from that X value, that gets us back to 0, and then we divide by the standard deviation, and that gets us back to a standard deviation of 1. In other words, if the standard deviation was 2 and we divide by 2, then that gets you back to a standard deviation of 1. So hopefully that you can sort of see that by applying that formula there, then that will get you back to something that has a standard deviation of 1 and a mean of 0. And then we can compare some things. Let's actually do the example because this will make a bit more sense when we do it. Okay, so I'll just leave that sort of sitting there. Okay, so let me do Jane first, right? So Jane. So Jane's X value, the value that she jumped 1.45 meters. So X is 1.45 meters. The mu for her is 1.2. And the standard deviation was 0.2. And so what that means, her Z score will be equal to X minus mu over sigma, which is 1.45 minus the average, minus 1.2, divided by 0.2. And if you think about it, that top line, 1.45, take away 1.2, that's how far above the mean she is. And then if you divide the mean by the standard deviation, that tells you how many standard deviations she is above the mean. Okay, so I'm just going to go put that into the calculator. So I can't do that in my head. 1.45 take away 1.2 over 0.2, and that's equal to 1.25. We'll talk about what that means. Equals 1.25. So what that means is that Jane is 1.25 standard deviations above average, above the mean. Okay, and so that gives us it gives her a score, a Z score, and that's a generalized, standardized score that we say to her, well done, you're 1.25 standard deviations above the average person. Well done. Well, good. Now let's see how Emily goes with the same test, right? So Emily goes with the same test, but remember, we're comparing her against year 10s. So her X score, how high did she jump? She jumped 1.83. And her average for her age group is I've lost it, 1.5. Year 10s, yep, and standard deviation of 0.3 for her age group. Okay, so therefore, what is Emily's Z score? Her Z score, X minus mu over sigma, is equal to her X was 1.83, take away 1.5, divided by 0.3. Again, chuck it all in the calculator. 1.83, take away 1.5 over 0.3, and she gets a Z score of 1.1. 1.1. And again, what that means is that Emily is 1.1 standard deviations above the average person. Okay, so who is better for their age? Jane is better for the age because her Z score is higher than Emily's Z score. Jane was 1.25 and Emily was 1.1. So to answer the question, Emily is better for her age. And I hope that makes sense because it's really hard to compare two normal distributions. But Z scores, if we standardize everything, and you can standardize any normal distribution, all you need to do is subtract the mean from it and divide by the standard deviation, and that gets you into a standard continuous random variable, and then you can do much more analysis from that. So Z scores are very well known across the place. If you hear people comparing things, oh, my test I got a Z score of 2.3, that means you're 2.3 standard deviations above the average person, and so that's very good. And so you don't need to tell someone what the average was or what the standard deviation was or anything like that. A Z score just takes all of that information out of it and just tells you how many standard deviations you are above the average person, or below for that matter. You could get a Z score of -2, meaning that you're 2 standard deviations below the average for your age group. Anyway, hope that makes sense. I'll see you in the next video.